Warm good evening to one and all present here, and we can start my session. My topic for today's session will be I'll be introducing you why quantum computing, transition from bits to qubits, what are the basic concepts in quantum world, various frameworks which are available, and some of the applications where QC can play a major role, and how to work with IBM Qiskit. We'll be talking about single qubit quantum gates, multi-qubit gates, and I'll be walking through quantum entanglement. These things I'll be showing the demo using IBM Qiskit. And adding up to my session, I'll also introduce how to become an IBM Qiskit advocate and benefits of becoming an IBM Qiskit advocate. So, one second. Ma'am, is my screen visible?
Yes, ma'am. Yes, ma'am. We got it.
Yeah, yes. So the main thing is the development of computing. Can I close this window, ma'am? Is this possible?
Top screen will be visible, ma'am, because of the participant list will display on the top.
Okay. I think it is gone. Okay. So, so the main thing is why we are moving on to quantum computing. The current day machines are classical machines. They work on a nature of irreversible logic, whereas quantum machines work on the concept of reversible circuits. And what Landrer and Feynman, what they have said was, current days systems are the major thing which we have is transistor sizes are shrinking, and systems generate heat is one of the major barriers of our current day systems which are being generated. So what people like Landrer said was, if at all, if we should have zero power dissipation, that is only possible if the computation is reversible. That is, we'll have a one-to-one mapping between our inputs and outputs, and vice versa. That is from outputs and also to our inputs. So in that case, that will not have loss of data, and that loss of data will not be generated as heat. And why we are talking about reversible computations are because quantum computing, it is inherently reversible, and all its circuits are irreversible in nature. So basically, this is from IBM's quantum machine, courtesy of IBM. Classical machines work on the principle of classical mechanics, whereas quantum computers work on the concept of quantum mechanics. And normal machines, we'll talk about something called as bits, where we have where we can be either in state 0 or in state 1. Whereas when I'm talking about quantum machines, we'll be having something like quantum bits, qubits. And qubit is not necessary that it should be 1 or 0 at a particular time. It can be both 0 and 1 at one particular time. So, and anywhere between 0 and 1 is also possible. And that is the advantage of working on quantum computers. So the transition from bits to qubits for classical computation works on the concept of either I can be in state 0 or I can be in state 1. Whereas when I'm talking about qubits, I can be my valid states. We use get bracket notation from quantum mechanics. So we can read this as ket 0 and this is read as ket 1. State xi is actually an arbitrary state xi is given by C1 ket 0 plus C2 ket 1. And we have one constraint that your squares of your amplitude, C1 and C2 are your amplitudes. So sum of your squares of your amplitudes should sum up to 1. So this is 0 state, this is state 1, and this is I'm in both 0 and 1. That is I'm in 50% 0 and 50% 1. So ket 0 is denoted, this diagram is Bloch-Spear representation, a Q-sphere representation. So we have this is 0, this is 1, bottom line will be 1. and in between. So I'm in both state 0 and state 1 at a particular time. So we are actually moving from bits to qubits when we work on quantum machines. I'll just have a scenario to explain why we are into quantum and why people are talking about quantum computing is, say for example, we are running a travel agency with 2 cars, taxi 0 and taxi 1. And there are 3 people over there. So tick indicates A and B are friends, B and C are enemies, and A and C are enemies. So we have tick goes for friend pass and cross goes for enemy pass. Since there are 2 taxis, and there are 3 people, the configurations are we have 2 to the power 3, that is 8 different ways in which these 3 people can travel using these 2 taxis. So here A, B, and C are person A, B, and C, and 0 and 1 indicates taxi 0 and taxi 1. So what we want is we would like to travel with our friends rather than with our enemies. So what the concept here is, if A and B are traveling in taxi 0 and C in another taxi, or if A and B are traveling in taxi 1 and C in taxi 0, is going to be two of our optimized solution for these 3 people to travel using these 2 taxis. So here we calculate the configuration score using the formula number of friends sharing the same car minus number of enemies sharing the same car. So if I'm considering this particular case 001, so we have one friend pair and there are no enemy pairs. Why? Because C is traveling in taxi 1. So we have 1 minus 0. So configuration score is 1. Similarly, for 110, we'll have 1. When I'm considering 101, A and C are enemy pairs and there are no friend pairs. So we have 0 minus 1, so which is minus 1. So we have all of these values, configuration scores, which are calculated for 3 people traveling in 2 taxis. So if suppose what happens, if I'm increasing number of people here, so I'm adding additional constraints of friends and enemies here. So A, B, C, and D. And we have 16 different ways in which these 2 people can travel. These 4 people can travel using these 2 taxis. So we can write a small C program or a Python program and calculate the configuration score and say whichever is going to give a higher result is going to be our best solution. So for 16 different ways, that is for 4 people traveling in 2 taxis, we can find. Similarly, now if I'm going for 100 people, rather than taking car, let me take bus. So we have 100 different people are there and they have to travel in 2 different buses with different friends and enemy pair combinations we are given. So we'll have around 10 to the power 30, which is 1 million configurations, which is impossible for us to solve on a regular classical computer. So if it is 3 people, we'll have 8 different ways. 4 people, we'll have 16. For 5, we'll have 32 configurations. For 100, we'll have around 10 to the power 30. So which becomes impossible for us to solve on a classical machine. But the same problem, I can solve it using a quantum machine in one operation of my time. So that is the advantage. So here, if I'm talking about a 1 qubit machine, I can compute on both 0 and 1 at the same time. If it is a 2 qubit machine, I can compute on all of these 4 values. So 0, 0, 0, 1, 1, 0, and 1, 1. This is our case for when I'm having 2 taxis and there are 3 people. So A, B, C are 3 different peoples. Taxi 0 and taxi 1 indicate 0 and 1 respectively. And I'm having these configurations. So 0, 0, 0 indicates all 3 are traveling in taxi 0. 1, 1, 1 indicates all 3 are traveling in taxi 1. This goes for A and B are traveling in taxi 0 and C in taxi 1. Similarly, A and B are traveling in taxi 1 and taxi 0. So we can compute on all of these 8 different combinations in one operation of our quantum system. So quantum computers work on the concept of parallel universe. That is, I can compute on 0 and 1 parallelly at the same time. So that is the advantage here. So the number of operations taken for solving our problem when I'm having 100 people, 2 buses with me, the number of operations on a classical machine is 10 to the power 30. Whereas when I'm talking about a quantum machine, I can compute on all of my configurations in one single operation of our time. So that is the advantage of quantum systems. Another example which I can tell you why into quantum computing is, say for example, if I have an equation y is equivalent to 2x square plus 4z plus 2. And if I'm computing the values for y, for various values of x and z, in one run of my program, I'll give one value of x, another value of z, and calculate y. So this goes on, okay? But if I'm taking in a quantum system, and I'm assuming my x and z are 3-qubit systems, so x can take value from 0, 1, 2, 3, 4, etc. up to 7, and z can also take values. Since it is 2 to power 3, 0 to 7, the values can be taken by both x and z. So what happens here is, in a quantum system, if I'm running this particular problem using a if I'm writing a quantum program to solve this, for all values of x and for all values of z. So when x is 0, when z is 0, what is y? When x is 0, when z is 1, what is y? When x is 0, z is 2, what is y? So for all combinations of x and z, I can compute the values of y in one run of my quantum program. So that is the advantage of quantum computing. The next part of my talk, I'll be talking about some of the concepts of quantum world. The first one is superposition. Next is interference, measurement, and entanglement. And these are some of the concepts. So superposition is I can be in both the states at one particular point of time. A quantum particle, an electron, or a photon can exist in multiple states at once. That is, I can be in two places and having two energies or having two energies at the same time. Say, suppose flipping a coin, the coin when it is flying on the sky, what happens is we'll be in both heads and tails at the same time until you look at it. So the same thing is superposition principle. I'll be showing the demo of superposition using IBM Qiskit. And interference is again dropping a stone into a well. So what happens? The corners gets destroyed, whereas when I'm having the more number of things, waves construct, and we'll have constructive interference. At the end, at the borders, we'll have destructive interference. So this is one. And the other one is measurement. Until I measure, my states can be in both the states. But when I go for a measurement, the quantum state collapses, and it can either be in state 0 or in state 1. Entanglement, again, I'll be showing using entanglement is something like twins can, a twin sitting here can identify what is happening to the other person on the other side. So that is what is entanglement, and that we can show or work on with entanglement policies. And there are many algorithms which depend quantum key distribution, many applications which are working based upon the concept of quantum entanglement. Quantum teleportation playing a major role in key distribution, quantum cryptography, and all of those. And basically the turning point of when quantum came into existence was when Peter Shor, 1992, he found an algorithm called Shor's factoring algorithm. What he said was, he can easily factor a very big number if quantum computers are into existence. Our passwords, our current day passwords work upon the principle of RSA, where we say we cannot factorize a very big number. So on that basis, so if I'm unable to, since we are unable to factorize, our passwords are safe. But once quantum computers, if everyone are using quantum machines, just like they're using classical machines today, you can easily break your passwords of anyone. So this was one of the turning point. And another turning point algorithm was Grover's search algorithm in 1994. What he said was, we can search a database in order of square root of n times using a quantum system. So that is advanced. So these two algorithms were turning points for quantum computing to boom. And people are talking about National Quantum Mission and so on. So all of these, and there are many algorithms, quantum Fourier transformation, quantum phase estimation, all other algorithms, uses Jozsa algorithm. Every algorithm plays a major role in various use cases which are currently people are working on. There are various quantum computing frameworks. First one, I actually started with QSharp, Microsoft QSharp. Like actually, I'm working in quantum computing from 2003. So when I started working, there were very few people from computer science perspective. That is mostly all of my when I was working for my MS, all of my people who helped me and supported me, they from either physics or chemistry background. So we didn't have any frameworks those days. So what we did was, what my work was, I worked on theoretical research, performing or calculating quantum query complexity for graph-based algorithms was my research. And later on, when I started for my PhD, there were simulators existing on those days. We had QCL, QDIT Pro, QC Viewer, where I should draw a circuit, check whether my circuits are working properly. So if I'm drawing it for 127 qubits, I have to draw it in hand and then check it through my machine, simulate it and work. So I designed a gate called as SMG gate on my name, which will work as a full ladder. So quantum gates, developing quantum gates, building quantum circuits, optimizing quantum circuits was my part of my research during my PhD. And 2017, Qiskit came into existence. So like I finished my PhD in 2015. So I would say I didn't work on Qiskit when I was working for my PhD. So the main thing which I have seen in this field is from theoretical research, moving on to simulators. Now I'm currently working on various real quantum devices. So that is how I've seen the growth of this particular field. So IBM Qiskit, I'll show you how easily you can visualize your various quantum states, your circuits, how to construct your circuits, optimize your circuits. And another very interesting platform where I'm working on is Classic. Classic, again, it's a high level quantum programming language, which is really very interesting to work on. If you're having, I don't have time to talk about Classic or work on Classic today, but if you're interested, you can just check this Classic platform. And if anyone is interested in working on quantum machine learning, I would suggest to work on Penny Lane of Xanadu, and Google is having their Circ. Circ is similar to Qiskit working and TensorFlow Quantum. And QSIM is India's product, Quantum Simulator. And all these are open source tools and they are free to use. So you can try these things. NVIDIA's CUDA-Q is also there. So there are many frameworks which are available currently in recent years. And various applications where you can use quantum computing algorithms are my area. One is designing reversible circuits. So circuits which we have are computer architecture, all Morris Mano textbook. Whatever circuits you're having in irreversible form, you can convert them into reversible nature one. Quantum software like Qiskit, Classic, Circ, Penny Lane, all of these people are investing more amount of their time in building up quantum softwares, quantum programming languages. And if you are circuit branch students or faculty members, I would suggest quantum hardware is very booming on. We are actually currently in the stage of earlier when we had classical computers in the existence, right? In that particular stage. So quantum hardware, many internships are available actually. Quantum machine learning. So whatever we have learned in classical side, we can find the counterparts in quantum. So either I could go for quantum machine learning, quantum image processing, quantum compilers, quantum games, quantum music. One of my friend is a very senior person of IBM. He's learning our Carnatic music to work on quantum music, generation of quantum music actually. And quantum finance and optimization. India startup people are working more towards quantum finance and optimization side. If interested, you can also check for quantum neural networks. You could find plenty amount of papers available on these topics, and there are many, many more. This is IBM Quantum Roadmap. So 2024, they introduced Heron, which goes for 5K and the number of qubits it supports. Okay. And Flamingo, it goes for around 156 qubits, 2025. And again, 2026, they are planning for reducing errors and they're going to support the amount of gates which circuits can support, 7.5K. And look at 2033 possibility of 2000 qubits. So when I'm talking about 2 to the power 5, 2 to power 2, it is 4. 2 to power 3, it is 8. 2 to power 4, it is 16. So 2 to power 5, it is 32. 2 to power 127, you can work currently. 2 to power 156. Imagine the amount of parallel operations which we can do if quantum computers of 2000 qubits comes into existence. Okay, so 2 to power 2000 is a aim for 2033. And this is a platform to work on IBM Qiskit. So quantum.cloud.ibm.com. I'll show you that in this demo. So how to run or work on. So things which are needed are, one, you have to talk about the number of qubits your circuit is going to have. And second part, what sort of combination of gates you're going to use to make up your algorithm. So you're building your algorithm using quantum gates. And then the qubits which you are going to measure and where you're storing. The storing of results will always take place on classical bits. So three things which we need for building a quantum circuit. One, the number of qubits. Next is a combination of gates. I'll be talking about gates in the later part of my talk. And what qubit we are measuring and where we are storing it in classical bits. So this is an example of a quantum circuit. Let me take this particular slide. So this slide talks about we are having Q0, Q1, Q2 and Q3. There are 4 qubits and there are 2 classical bits. And what are these is our algorithm. So these are our inputs. I'm applying quantum gates onto my qubits. So X is one of your quantum gate. And these again, some more quantum gates, CX gate. I'll be talking about these gates. So this is your algorithm which you're going. So this is your input. You do some process and you measure. These two symbols indicate they are measurements. So we are measuring Q2 and storing it in classical bit 0. This indicates classical bit 0 and measuring Q3 and storing it in classical bit 1. I'll repeat once again. For a particular quantum circuit, we should do the number of qubits and the number of classical bits. And you work on with the algorithm or what input you're giving and how what is your process you're doing. And at the end, measurement of your outputs and measure your qubits and store it in classical bits. Why? Because if I measure my values of my qubits, they get collapsed and they can either stand in state 0 or stand in state 1. So that is that. So this is, let me go for the demo part. So this is the platform which I was talking about, quantum.cloud.ibm.com. So I'm just signing in. If you're a new user, you have new to platform, create an IBM cloud account. Ma'am, I just have one question. Did any of the speakers spoke about IBM Qiskit? Can anyone answer me?
No, madam.
No. Okay, sir. So if you are first time users, you can go for creating an IBM cloud account here. Let me just log in with my account. You can use US East here. I'm just continuing.
Ma'am, I have one question. This is
Yes.
free for the users
Yes, ma'am.
first time?
Yes, ma'am. Yes, ma'am.
Okay. So we must have some limited access, no, for this?
Like actually, so Composer all it's free only, ma'am. For only like I would say, I'll show you. I'll tell you where you're supposed to pay. Right now, it is free. If I'm executing on devices only, I have to pay.
Okay, ma'am.
If I'm not executing on devices, if I'm executing it locally, no issues. You need not. And that too for beginning stages, that is earlier researchers need not, you need not pay for the current moment. Earlier it was fully free actually, but now they are charging your, if I'm using on devices like IBM_Torino for seconds, and they offer you monthly how many minutes you have, and there are paid plans also. But for the moment, it is not needed, Mama.
Okay, ma'am. Yeah, thank you.
Yeah. So I've just logged into my system, into my login. And here you could see documentation, tutorials. This is free right now. You need not to bother about paying and learning about. For tutorials, for learning, browsing tutorials, all, it's really, you have lot amount of things to learn from this particular site. So let me start with Composer. Let me open it and unmute that. So this is our dashboard here, and Composer allows us to go for 4 qubits maximum. So 2 to the power 4 different values you can work. So look at the values here. If it is for 4, I'm just deleting some of my qubits. So just go select there. That's it. So I'm just talking about, let me, if you want, I can show you 2 to the power 3. So 0, 0, 0, etc. up to 1, 1, 1. Okay. So if there are 2 taxis and there are 3 people with us, I can apply some quantum gates and I can put them all in various. This is one of our important quantum gate actually. So I'm just don't worry right now. So right now what is actually happening is I'm in state 0, 0, 0. I'm in state 0, 0, 1. I'm in state 1, 1, 1. And I'm computing on all of these states. I can add on my algorithm. And for all of my quantum states, from 0, 0, 0 to 1, 1, 1, I can compute on all of these. So if it is my travel agency problem, 0, 0, 1 is going to be my solution and 1, 1, 0 is going to be my solution. So those 2 solutions will have highest amplitudes and for all others we'll have 0. That is how your algorithm will work. Okay, so what is actually happening here is, this is your dashboard which is containing various quantum gates which are available. I'll be talking about these quantum gates in my next part of my talk. And this is your dashboard where you drag and drop your quantum gates. Just pull them and have it. If you don't want anything, you can select and use delete, or keyboard delete button will also work. And here, the right part of my screen is, we read this as CASM. CASM code is auto-generated for us. So we use OpenCASM 2.2. The included library header file is this, and quantum registers. So how many qubits we are having, so register, and how many classical registers we are using. So if I'm deleting here, if I don't want 2 of my classical bits, I'm just having. So you could see if you delete here, this also gets updated. If I can also do it here, both the ways it's possible. So I've given C of 1 here, so this is also possible. That is, they are dynamic. Whatever changes I do on my circuit dashboard, that will also work. Or if I'm doing it this side, this will also work. The next part is the gates which I'm applying. So I'm applying Hadamard gate on qubit 1. I've applied Hadamard gate on qubit 2. So this is how it's working. So right now, don't worry about your quantum gates. What we have done. So we have a dashboard of various quantum gates, available quantum gates here, and you can drag and drop your quantum gates once you know how these quantum gates works. And then this is the code which is auto-generated for us. And setting up and running it, obviously you have to add a measurement to run, and you can run your experiment using these things. So and one thing which I thought of talking about is quantum programs. For the first run, they might give me my first best solution. But when I'm running my program for the second time, it might give me second best solution. So sometimes it will give you second best solution, third best solution, and so on. Why? Because due to errors in current day quantum machines. So what we are suggested to do is run for more number of shots. You're going to write one program, and instead of running it for one shot, I'll be running it for more number of shots. Say I'm running this program for 1024 shots. So for 1024 shots, I would take up the probability of values. So for 1000 times, if my answer was 0, and for the rest of 24 times, if my answer was 1, we'll take our solution as the majority, the highest one, whichever is largest, that you will be taking. So this is things. And look at IBM Brisbane, which I'm having. This supports 127 qubits. And the current number of pending jobs which are right now is 2048. So if I'm submitting a job, I had to be wait on queue. Again, similarly, IBM Torino, which goes for 133 qubits, it supports Heron processor, and there are pending jobs which are available right now is 415. So right now I'm not running because we are having restricted amount of time, so I'm not running up my jobs. Once we are familiar with building up a building knowledge of quantum gates, build your circuits, and then what you're going to measure and how you're going to run. So those things you can, and you can run it on the various devices which you have. Earlier, what we had was we were able to work on various simulators which were available for free. But now it is simulators are removed, and we are only allowed to run it on these devices. But for learning out or looking at the outputs, I would suggest it is enough if I go for the probabilities. Your Q sphere is one output representation which we have. And we also have a state vector representation. So this is your state vector representation. So scrolling down of the screen, you could see the state vector values. So initially we should know what state vector is, how you can go for your Q sphere, what is Q sphere, and so on. So for that, let me introduce some of the quantum gates, and then I can talk about the various outputs representations which we are having right now. Any doubts for the moment? If you're having any doubts, you could, or shall I take the doubt questions at the end? So moving on to my next part of my talk, here we are having reversible circuits, a small illustration of comparison of irreversible circuits and reversible circuits. This is AND gate. Irreversible AND gate. If the value of A and B was 0, it is impossible for us to say what your A or B was. That is, I can't predict whether A was 0 or B was 0 or A was 1 or B was 1 because they are irreversible in nature. So this is the drawback of our current day classical machines. So we are losing our inputs. Inputs are given, we get our output. After our generation of outputs, we lose our inputs. And that loss of data, input data, is actually generated as heat. And that's what various scientists said, that if this loss of data is not, if it should be minimized, the only possibility is the circuits have to be in reversible in nature. So reversible is, we have one-to-one mapping between inputs and outputs. I can walk from outputs to inputs, inputs to outputs, and we are not going to lose our data even after taking up our measuring our outputs. So, and all quantum circuits are reversible in nature. That is one of the major advantages. So here, from here, I'll be starting off with various quantum states, how to represent them, starting from gate 0, gate 1, and so on. So basically, we have 3 different bases. So one is Z basis, second one is X basis, and third one is Y basis. So in Z basis, we'll talk about 2 eigenvectors, gate 0 and gate 1. If you are interested, note down what is gate 0. Gate 0 in matrix representation is 1, 0. And for gate 1, we'll take it as 0, 1. Okay. So gate 0 and gate 1, we are representing our qubit states using vectors. For the moment, I'm just talking about gate 0 and gate 1 in this particular slide. So we just take out this. And a valid state Q is given by, no need of math, but if you are interested, cos theta by 2 gate 0 plus E I phi sin theta by 2 gate 1. Your phi goes for amplitude. Next is the Z basis, your eigenvectors are gate 0 and gate 1. Next, for X basis, your eigenvectors are plus and minus. So what is plus? A plus is 1 by root 2, gate 0 plus gate 1. I am in both of my states with the positive amplitude of state 1. So gate 0, 50% I am in gate 0, 50% I am in gate 1. The vector representation of your state plus is 1 by root 2. 0 is also 1 and 1 is also 1. For minus, this is 0 plus 1 divided by root 2. Just opposite to this is your state minus. So 0 minus 1 divided by 0 minus 1 divided by root 2. That is gate 0 minus gate 1 the whole divided by root 2. Or using vectors, We can take it as 1 by root 2, 1 minus 1. There is also another basis called as y basis, and we take your eigen states as plus I and minus I. So 0 plus I1 the whole divided by root 2, and for minus I, I'll take it as 0 minus I1 the whole divided by root 2. So the vector representation for plus I is 1 by root 2, I by root 2. For minus I is 1 by root 2, minus I by root 2. This is superposition. Superposition status, we are going to be on both the states. So earlier in that basis, I can be in state 0 or in state 1. But when I'm putting my states in that basis to exist in both the states, I can go for creating superposition between our qubits. So we have alpha kit 0 plus beta kit 1. And sum of my alpha square plus beta square should sum up to 1. This is one of the major constraint for a particular valid quantum state. So the measuring of these probabilities, squares of their probabilities should sum up to 1. And I can have 0 to be full 100%, beta, that is alpha to be full 100, beta to be 0. In that case, I'm in state 0. If it is 50-50, I'm in state 0 and I'm in state 1. If beta is full 100, I'm in state 1 and we are not there in state 0. This is for single qubit superposition. But as a multi-qubit states, so two states we are having 0, 0, 0, 1, 1, 0 and 1, 1. So 2 to power 2. So on all four combinations. So sum of your squares of your amplitudes, A0 plus A1, A2, A3. Sum of my squares of my amplitude should sum up to 1, measuring each state sum to 100%. If I'm talking here, I could say this is 25%, 25%, 25%, and 25%. And this is Q-sphere representation actually. I'll show these things in demo for you. So some of my quantum gates which are available. So QC is your quantum circuit. And X denotes what quantum gate, and 0 denotes onto which qubit I'm applying actually. So we have X, we have Y, Z gate, S gate, S dagger gate, SDG, and we have Hadamard gate. So I'll be talking about X gate and Hadamard gate and show you the demo of those gates in using Composer. So single qubit gates, this was worked and we have done here. So I'm taking, if you're interested, you can note down the slide. So plus state is 1 by root 2, 0 plus get 1. Minus state is 1 by root 2, get 0 minus get 1. And for I and minus I, interested if you want, you can take. I want plus and minus to be taken down. The Hadamard gate matrix representation of Hadamard gate is 1 by root 2, 1, 1, 1 minus 1. And if I'm applying Hadamard onto my state 0, it will take me to my plus state. What is my plus state? My plus state is this. So if I'm initially starting in 0, and if I'm applying Hadamard gate onto my state 0, it will take me to my state plus. What is my plus? My plus is 1 by root 2, 0 plus 1. So Hadamard gate is the one which is used for creating superposition of states. So I'm in both of my states, right? I'm in state 0 and I'm in states. You to create a superposition state means the other one is Q-sphere representation, and the third one is state vector representation in my composer. Then I've thought about talking about X gate also. So X gate matrix representation is this. If you are interested, you can take up this. And X on 0, X is actually a NOT gate, a classical NOT gate. So X on 0 will take us to 1. X on 1 will take us to 0. X on plus will remain me in plus. X on minus will take me to minus of minus. And I and minus I. So what are these? 0 and 1 are your eigenstates on Z basis. Plus and minus are eigenstates on your X basis. I and minus I are eigenstates on your Y basis. So for all of these inputs, 0, 1, plus, minus, I, minus I, I can apply my quantum gates. So I can apply X gate, I can apply Y gate. This is after working. We have given the various for what input, what output you will get. So X gate and Hadamard gate I'll show you in Composer. Similarly, we have Z gate